streaming, as well as shutting off any extraneous programs, including my fun beach video, just to make sure that we can try and get the best record of class. So without further ado, let's talk about formative assessment number 4, shall we? Why not? So the first question is something that we didn't spend a lot of time on, but it's something that I wanted to make sure that we return to because it's important to recognize when you'll be able to do this stuff in practice that we're learning and when you're going to need to invest in additional technology to be able to analyze the kinds of research data that you're interested in. So the three assumptions about the model residuals. So several of you reminded me what a model residual is, which is always helpful. So we're talking about the E sub I term, so E for each person. E is the difference between what the model says your outcome is supposed to be and what the data say. So how far off of the regression line or how far off of the group mean, that's what E represents. And as we add predictors to the model, the variability of the E's across persons should go down. So the question is, what else needs to be plausible about the E's in order for our results to be believable? There's three main assumptions that I want you to be familiar with that go into general linear models about the residuals. Number one is that they're supposed to be normally distributed. So when would this get broken in practice would be when you're analyzing outcomes that are not continuous variables. So for instance, if you were trying to predict a binary outcome variable, there's no way that the E's are going to be normally distributed. The same would be true if you were trying to predict an ordinal outcome or an outcome that has boundaries, like proportion correct, something like that. And so for those situations, you would need to turn to potentially a different model, the family of what is known as generalized linear models. So we're talking about general linear models specifically. Generalized linear models are models for different kinds of outcomes besides normal. Another is that the residuals are supposed to have constant variance. So that's the idea of homoscedasticity. The model is supposed to work equally well for everyone as a function of the predictors or the predicted values. So if you see, for instance, that the residuals have more variability at higher levels of your predictor, like that fan shape, that's potentially a problem with constant variance. This one is trickier to address, but you would need to look for models that allow you to specify that the variance can change. Some of the some of the generalized linear models do that. It's a built-in option that allows the variance to increase as a function of what the predicted value is, for instance. And the third one, so we have normality of the residuals, constant variance of the residuals. The third one is independence. And that's the idea that the E from any two people should not be more related than E's from other two people. When would that be violated? Well, whenever you've sampled people from intact groups. So for instance, if you sampled children from multiple classrooms, the E's of children from the same classroom are probably still going to be related even after you put all of the predictors into the model that you care about. And so that's going to violate the assumptions of the model. Likewise, if you collect multiple outcomes from the same person and try to analyze them all at the same time, the E's from the same person are going to be more related than E's from different people. The solution to that is another model, what's known as multi-level models or mixed effects models. And so those are the additional classes that I offer as well. So the bottom line of this is that the take-home point here, if your data don't fit the assumptions of the model, you need a new model. It's less preferred to try to force the data into a model in which they don't fit. So in certain circumstances, for instance, if you have skewed outcomes, for instance, if the residuals still look skewed, a log transformation on the outcome can make them look more normal. And if that's the only problem that you have, that may be a reasonable solution. But there are models that are built to address each of these limitations and expand the model to be able to better match the data. So the take-home point is that if these three things are not true, you may need a different model. That's what I want you to, the idea isn't to fix the data, it's to pick a new model. It's like those t-shirts that say, one size fits most, right? They don't usually fit anybody. So you just need a different size if the model doesn't fit. So any questions or comments on that one? Okay, one more thing I just forgot I was going to mention. A few of you wrote down that X and Y have to be linearly related. That is only true if that's the model that you fit for how they're related. So more generally, what you're assuming about the residuals is that whatever is left over, the residuals, they're unrelated to the predictors because you have fully specified all the ways that X relates to Y. So if you just put in a linear slope for X in predicting Y, then you are assuming that they're linearly related. If you put in a bendy slope, like a quadratic effect by adding a squared term we talked about at the end of last week, then you're assuming that they are quadratically related, not linearly related. This week we'll get a chance to see yet a third option, which is known as linear splines, or different slopes through different sections of a predictor, which is another way of describing a nonlinear relationship. So more generally, you're assuming whatever you put into the model, not necessarily linear if you've added terms that allow for a nonlinear relationship. So does that make sense, the distinction? Maybe? Okay, I'm getting stares, not nods, so I'm going to take that as a no. Basically, whatever you say in the model needs to be true, or your results are not going to be correct. How's that? And by results, more specifically, it's the standard errors. The point estimates, so what the number is that comes back for what your slope is, that's probably going to be fine. It's the standard errors that are messed up. So when any of these assumptions are violated with respect to the residuals, the problem comes within the standard errors. And if your standard errors are messed up, your p-values are messed up. So it's the inferences from the model that are potentially problematic if the residuals don't follow the rules that they're supposed to. So just keep that in the back of your head as you're going about this. So thoughts or questions on any of that? All right, next. Okay, so question 2 is looking at the relationship between T, F, R, and R square if there's only one slope in the model. And I am pulling this directly out of this slide right here. This is lecture 4, slide 16. What I'm looking for you to recognize is that if you only have one slope in the model, so that would happen if you are specifying a linear effect of your X predictor as predicting your Y outcome, or that could also happen if you have a binary X predictor, and so there's only two groups, such that you would only have one mean difference between the two groups, one slope. If you only have one slope in the model, the significance test for that slope tells you the same thing as the significance test for the model. So T is the significance test used for a single slope. T squared gives you the F test for the model. So there's a one-to-one correspondence between the model and the slope if there's only one slope. Likewise, the effect size for that slope in an R metric, which would be a Pearson correlation if there's only one slope, you square that R and that is the model R square. So the only situations in which we need to pay attention to F and R square as giving us new information is when there's two or more slopes. And then F and R give us a test and effect size, respectively, as to how those two slopes work together to create a predicted outcome that is correlated with the real one. So F and R come into play when there's more than one slope in the model at the same time. So that can happen if you have, say, a linear and quadratic effect of age. That can happen if you have three groups, which takes two slopes to distinguish them. That can happen if you have an X predictor and a Z predictor, for instance. So there's lots of instances in which you'd have more than one slope. That would be the bulk of the time, actually, in which case you want to pay attention to how well the model works as a whole, which is tested by F. The effect size for that is R squared, the proportion of variance accounted for, also known as the square of the correlation between the y hat predicted by the model and the real y in your data. Both of those are true. Okay, questions or comments on any of that one? Okay, and then last but not least, this one. So the last question is setting you up to be able to do section 1 of your homework 4. So not a coincidence that I'm asking you to go from a 3-group example to a 4-group example. So I wanted to spend a little bit of time on this one in particular, making sure that you understand the logic of what's going on. Because if you understand the logic, then the question just becomes, okay, how do I make SAS or Stata do this? But understanding what you're trying to do in the first place is the beginning step. So first here, if I have a GLM with a single categorical predictor with 4 categories, so there's 4 groups to be distinguished here. Categories and groups, by the way, are synonyms in my vocabulary. By what other name would this analysis be called? So several of you got this right. You can give me the acronym or you can write it out. What am I calling this? If I have a categorical predictor of a quantitative outcome, yes, ANOVA. That stands for analysis of variance. More technically, you would call this a one-way ANOVA, that you have one factor, as it is known. So those of you in the design class, you would know this as a one-way ANOVA. If you had 2 grouping variables in the model as predictors at the same time, that would become a two-way ANOVA, but just one set of groups. So one construct where there's 4 possible groups you could be in, that's one-way ANOVA. Given a single model intercept for a reference category, how many fixed slopes would we need in order to be able to differentiate the mean for all 4 categories? Yes, this is a hold your hand up and vote question. How many slopes do we need? There's 3. Yeah, it's always the number of categories minus 1. That's how many slopes you need. So if I have an intercept, the intercept is going to give me the mean for the reference group. So that's one parameter. The first slope is going to get me to the second group. The second slope is going to get me to the third group. And the third slope is going to get me to the fourth group. Now I've got all 4 means given to me by 4 fixed effects, which is an intercept for everybody, and then 3 slopes that bump me up to each of the other groups. So we got 3 slopes to get us all 4 means. How many pairwise mean differences are possible? So pairwise means between each set of 2. Yeah, this is another hand vote, or you can type your choice. Yeah, 6. There's a formula for it. N choose K is a formula for combinations that you may remember from whenever you would have learned that. I'm not sure how long ago it is. And if you don't want to use the formula, you can just count on your fingers, right? We have group 0 versus 1, 0 versus 2, 0 versus 3, 1 versus 2, 1 versus 3, and 2 versus 3. That gives me 6. So how many of those are going to be given by the model directly, and how many of those need to be found as linear combinations? So there was less certainty on these last 2. Yeah. So yeah, the answer is the same for each. There's 3 direct and 3 indirect. Now where did that come from? Well, because you already answered correctly how many slopes we need. The job of a slope is to give me one of the mean differences. In this coding scheme, that's how we've set it up. So each of the 3 slopes that we're going to put in, its job is to get from the reference group to each of the other groups. So that's 3 of the 6 mean differences right there. That means that the other 3 have to be found as linear combinations. So the last 2 answers are 3 and 3. Okay, so are you okay with the logic? Just this much as a concept? Or is any of that you want to hear again or talk about more?
Yeah, I'm sorry,
Yep.
can you say that one more time? D and E?
Yes. The answer to each of those is 3. So 3 of the pairwise differences are given directly by the model, and 3 of them are linear combinations of the model fixed effects. So the 3 that are given directly by the model are the 3 slopes, because the job of each of the slopes is to go from the reference group to each of the alternative groups. So those are the 3 mean differences given directly. It's the differences between those slopes that indirectly then give us the remaining 3 possible differences. So the model gives us all 6. 3 of them are given sort of obviously, directly, and 3 of them are less obvious because they are required to use linear combinations to get them. And I wanted to show you the latter again to make sure that you understand how that process works. Okay, so I have built another little uh, spreadsheet here. This is how we write on the chalkboard during a pandemic. We open up Excel and type into it. And yes, I will post this after class. So let's first fill out my little table here. So this would be what it would look like for a 4-group example, such as in your homework. So I've got 4 groups here. They're labeled group 0, 1, 2, and 3, because what the groups stand for doesn't actually matter, right? This is just sort of a generic 4-group example. Um, in this example, I would like to make it so that the group that is number 0 here is going to be my reference. So that tells me then what the values of the 3 predictors that I need to create must be, because the reference group needs to be coded 0 on each of these. So what I'm doing now are creating 3 new predictors whose slopes are going to be estimated directly by the model. So the model that I'm creating looks like this over here. Y equals beta 0, the intercept, plus the effect of G0 versus 1, the effect of G0 versus 2, and plus the effect of G0 versus 3. So 0 as the reference versus each of the others. So if I put zeros everywhere here, that sets group 0 as my reference. Now to make the first column here, to make this variable represent the difference between group 0 and group 1, what goes in this cell right here? Yeah, this is another hand gesture one. I need a 1. The others get zeroed out. So if we look at just this much, can you see where I've highlighted? Okay. We started with just that much when we first did this for a single binary predictor. So in our example 3, we had married people versus unmarried people predicting income. And in homework 3, I had you look at the number of fits thrown for 3-year-olds versus 4-year-olds. So the part that I've highlighted here, if you only have 2 groups, you only need 1 predictor that differentiates them. One of the groups gets coded 0 and one of the groups is coded 1. So we're talking about how to extend the coding scheme to incorporate more than 2 groups. Now this column, if I want this column to give me the difference of group 0 versus 2, then what goes here on the line for group 1? They're zeroed out. What goes here on the line for group 2? They get the 1. What goes here for group 3? 0. Last one. If I want this column to give me the difference between group 0 and group 3, what goes here on the line for group 1? 0. What goes here on the line for group 2? 0. That must mean we pick up the 1 on the last one. So this is all you need to know to do everything else. Everything else in terms of the code follows from this system of zeros and ones. And this system of zeros and ones in turn makes it so that you can interpret these parameters in the way that you're intending. So the choices that you make in terms of who's the zero and who's the one then dictates what these effects actually mean. So I would take these three new predictors and they go into the model. Okay, they are specified. Here's the two lines. One is from SAS and one is an example from Stata. They go into the model as predictors. The original group variable is done. Okay, that doesn't go in. That is a nominal variable, not what we need to analyze. So we're sticking with the three new variables that we made as the predictors in the model. Okay, with me so far? So now statements. How do we get the model to tell us the things that we want to know? So if I go back to the original question here, we need to know four means, right? We want to know what the mean is going to be for each of my four groups. And there's 6 possible mean differences. So an estimate statement to get the group means would look like this. For instance, here's the group 0 mean. What it's doing is filling in values that correspond to the model equation. Question, but before you do that, do we need to create names for them? Do you mean the names of the new variables? Because yes, you do.
Yeah, I meant the names of the new variables before you can assign numbers.
Yes. So the code to create the new variables would be something like if, in SAS, it's like if group equals 0, then do G0 versus 1 equals 0, G0 versus 2
Mhm.
equals 0, and so forth.
Is the if statement coming after?
In Stata, it does.
Okay, but in
So
SAS not.
yeah, so in Stata, it's like replace group G0 versus 1 equals 0 if group equals 0.
Okay.
So you can follow the code to do this. Well, the first example in example 4 has a 3-group version. You can follow the structure of the code and just add one
A
more
four.
new variable to the set. Okay, does that help?
Yeah.
Okay, yes, thanks for the question. Okay, so this model equation then tells us how each of the group means is going to get made. So here's one for the control group. I need one beta 0, and then I need to fill in the values for whatever we did for group 0 for my new predictors. And that's why the 3 new predictors have zeros after them, because that corresponds to the coding scheme for group 0. Question, if you are comparing group 1 versus 3 and 2 versus 3, do we need to create variables for them also? No, we do not. They're already in the model as a linear combination of the differences relative to group 0, and that's what I wanted to show you. So if I want to do group 1's mean, I still need intercept 1 because group 1 gets a beta 0, everybody gets a beta 0. They need a 1 after the first predictor because they get a 1 in the coding scheme. The other two predictors stay 0 because that's how it is in the coding scheme. If I do group 2, the first predictor goes back to 0. The second predictor switches to 1 because that's how it is in the coding scheme. And last but not least, group 3. Come on. Where the last fixed effect turns on instead. So the same grid-like pattern of ones on the diagonal is in both places. Okay, does this much make sense? Yes, okay. Now the differences. Here's the trick. Once you get this part right, you're home free. Because if you know how to get to what each group's mean is supposed to be, you know how to get their differences. So the ones that are given to you directly, there's 3 group differences out of the 6 that you already have. You don't have to write anything for them. And they are given directly as the betas. So on your output, the slope coefficient that goes with G0 versus 1, for instance, because of the way that we've coded this, I know that the slope for G0 versus 1 automatically tells me how the 1 group differs from the 0 group. That's what it means. So if the slope is positive, that means the group coded 1 is higher than the 0 group. If the slope coefficient is negative, the group coded 1 is lower than the 0 group. Likewise, the other 2 predictors that I made directly give me 0 versus 2 and 0 versus 3. So the fixed effects that are already given to you as model parameters, the slopes that are being estimated that you asked for because you put these predictors in the model, those resulting slopes are already giving you group 0 versus each of the 3 others. So that's the 3 that are given. Okay. To get to the others, we will literally subtract each between these lines. So if I wanted to know, for instance, 1 versus 2, I already figured out how to get to the group 1 mean, and I figured out how to get to the group 2 mean. I've got them right here. I need their difference. I need to subtract. Order of operations matters for direction. I'm going to start with the group 2 mean, and I'm going to subtract from it the group 1 mean. I'm going to put a minus sign out here. Nope, that's right. Excel doesn't like it when you just put in a minus sign. So that's the word minus. Let me squirt over a little bit here. We just need this much right now. Okay. So if I want to know the difference of how group 1 is versus group 2, this is what I need to do. So estimate group 1 versus 2. Okay. What is intercept 1 minus intercept 1? 0. So they cancel. So I don't need anything for intercept, but I'm going to leave it here as a placeholder so that you can see the alignment. Next one, for group 0 versus 1, what goes here? Yeah, you need 2 hands on this one. This is a minus sign. Yeah, 0 minus 1. And no, these don't have to be aligned, but it will make your life easier if you line these up so that you can see the pattern. How about here, group 0 versus 2? What goes here? 1 minus 0 is 1. And group 0 versus 3, what goes here? 0. Semicolon. There. Do you want to do 1 versus 3? Do another one? Yeah, we'll do one more. Let me make a new line here. I'm going to swap out 3 versus 1. Okay, so 1 minus 1 is still 0. 0 minus 1 is still minus 1. 0 minus 0 goes to 0. And 1 minus 0 goes to 1. So once you do a couple of these, you'll start to see the pattern. Basically, it's the two slopes that have to do with the groups being compared, where the slope that goes with the group that's the reference, the one that goes before the versus, gets the minus, and the one that goes after the versus gets the 1. And there'd be one more set. Should we do the last one? Why not? I'm feeling generous. Group 2 and 3. So intercept still drops. This one goes to 0. This one goes to minus 1. And the last one stays at 1. So yes, the indirect comparisons would be the differences between the non-reference groups. They're implied by the model, but they're not given directly. You just have to know how to ask for them. Kind of reminds me of secret menus at fast food places. Have you heard of this? There's certain places where there's things that you can ask for. Like, I think it's In-N-Out Burger in California. There's a secret menu. You can ask the Google about this. There's a secret menu for every fast food restaurant. There's things that you can order that the people who work there will know what you mean, even though it's not on the visual menu in front of you, because it uses ingredients that the restaurant already has, and it just puts them together in a new combination. That's like this. Think of the estimate statements for the indirect model mean comparisons here as like your secret menu. It's in there. You just got to know how to ask for it. All right. So questions on any of that before we switch gears?
Yeah, actually, I do.
Sure.
So just to clarify, like the estimate, the first part where we're looking for the direct one, those are actually the intercepts for the that correspond to the fixed slopes, right?
Do you mean these things right here?
Yes.
These are the model implied group means. So they each have the intercept as a component of it, but to get to the mean for each group, it's the intercept plus the effect of the slope that differentiates that group from the reference. So the last three here, these are given as linear combinations because each one is intercept plus one of the slopes.
So it's kind of like, so for example, the second one is the G0 versus 1 and times the B1. That's what you're getting at, right?
The words in here, these words refer to their betas in the equation. So whatever the slope ends up being is going to be multiplied by the 1 that you put here. And the reason that you put a 1 there versus a 0 goes back to your coding scheme over here. So the constants that you're entering here have to do with the value that the predictor takes on when it's conditional on that group. The words themselves are placeholders for the corresponding beta, the slope coefficient that goes with that predictor.
Okay.
So it's confusing because it's somewhat non-intuitive. The words go with the betas, the numbers go with the values of the predictor. So the zeros and ones that we're filling in, it's what are you putting for the term that's in parentheses? That's what the zeros and ones go with. The multiplier of the term in parentheses, each of the betas, that's whatever it's going to be after estimating the model. So you don't have to know what the result is ahead of time to be able to use these statements, which is what makes them handy. No, I'm making it worse, aren't I? Yeah, at some point there's a quadratic effect of talking, right? Like Lisa's explaining something and you start to feel better, and then Lisa just talks too much and it goes back down the other side. I got to learn where the asymptote is and just figure out where, when to shut my mouth. But maybe now would be a good time.
Can I
Okay.
just ask one more point of clarification?
Sure.
So for our code on this, are we going to write out all these estimate lines of code or just the last one in the group?
You will need to write out, so like of these
I know.
4, for instance, you don't have to write the first one because that one is given directly by the intercept. That's already in your output. You do have to write these 3, and you would have to write the last one,
Okay.
right, in each of the series.
Okay, great. Thank you.
I was just trying to show you more explicitly what is subtracted from what.
Yes. Okay.
Okay. Other questions? No? Okay. So I recorded the remainder of the lecture that got cut off unexpectedly about quadratic effects. Is there any of that you guys want to talk about in terms of being able to fit the linear and quadratic effects of a quantitative predictor? Let me go back to the slides here. So the idea is to be able to fit a model. Let me find the slide here. This is slide 23. That looks like this. So the quadratic effect of a quantitative predictor creates a regression line that's bendy, at least to some extent. So it has a U shape in the most traditional form, but it can be sort of bendy towards the top or bendy towards the side. In practice, the model predicted quadratics tend to look like one of these 4 shapes. So in your homework, I'm asking you for 2 of the questions to figure out which of the 4 shapes you're looking at. Do you have a positive slope that becomes more positive, a positive slope that becomes less positive with a negative quadratic, a negative slope that becomes less negative, or a negative slope that becomes more negative? And the trick to interpreting quadratic effects correctly is remembering that the slope for the linear term, so the predictor entered all by itself, that linear slope is conditional specifically when that predictor is 0. So in our example, for instance, here is slide 28. Let me hide the controls here so we can see this a little better. These are the results of the model when fit to the example data that we've been playing with, so predicting income from age. In this example, age is centered at 18. So that means that my intercept, which was estimated at 2.6, that is the predicted Y for an 18-year-old specifically. And I know that because the intercept is always the predicted outcome when your predictors are 0. And that happens in this model. These 2 terms get zeroed out if age is 18. So if age is 18, the only term that contributes to the predicted outcome for an 18-year-old is beta 0, the intercept. So the definition of beta 0 in this model is as the predicted Y outcome for an 18-year-old. Likewise, because of the squared term, so because of this quadratic term of age multiplied by itself, the effect of age, the linear term, so just the straight effect of age, that slope of 1.2 is specific to an 18-year-old. So at age 18, for every year older you are, you make $1,200 more according to this model. The quadratic coefficient for age squared is negative. So this is a combination that gives us a positive linear slope that becomes less positive. So yeah, as you get older, you make more money up to a point. And you can actually figure out at what point the curve changes directions, at what point the linear slope instantaneous at that point is 0. And here's the equation to do that down at the bottom. It works out that 48 is the age at which income is maximum, and after that, it goes down. So I'm giving you these additional predictions just to illustrate how the model works. This is not something I'm asking you to do in your homework. So in your homework, I'm asking you just to fit a quadratic model and to tell me for each of the slopes whether it's positive or negative, significant or non-significant, and to recognize which of the 4 kinds you have. More positive, less positive, more negative, or less negative. What does the quadratic do to it? And one more thing, homework question. Quadratic slope needs to be multiplied by 2 to describe what happens to the linear slope as x increases. The actual quadratic coefficient is half the rate of acceleration or deceleration of the function in physics terms. So multiplying by 2 is the one thing that makes this tricky. And I think that was all the stuff that I reiterated in my video. So questions on any of that? Okay. In your homework, I'm asking you to leave your predictor uncentered because 0 is already near the mean of that predictor variable. So that's one less step in terms of having to subtract 18 or any of that. You don't have to in homework. All right. Then we can look at something new if there's no other questions. Picking up on slide 31. Welcome to linear splines, or what I refer to as piecewise models. So let's look at this picture. Pictures are good, right? Pictures are better than equations in SAS code. I figured you'd feel that way, so I made you a picture. So I made this picture in SAS. The code that I used to do so is online in case you wanted to play with it. What the black line here is showing is the mean income level for each unique value of years of education in the data set. So the way that education is measured is in integers, years of education, where we can guess, based on the fact that this is a US sample, that 12 years of education would correspond to a high school degree. It looks like 16-ish corresponds to a bachelor's degree. And then there's some fuzziness out here as to how many years would hit to the next degree, but it sort of looks like master's would be 18, and then after that you're in 20th grade with, whatever happens after that point. So previously, in example 3, we fit a model that had a linear slope of education predicting income. And this picture suggests that a linear slope is not going to fit. It's not the case, according to the data and according to common sense, that having one more year of education is going to get you the same gain in income. So it's not the same if going from 9th grade to 10th grade as it is from going from 11th grade to 12th grade. 9 to 10 doesn't get you another degree, but 11 to 12 does. And so the acute jump that you can see here from 11 to 12, 1 year of income at that point on the variable means more than 1 more year of income previous to that. Likewise, after 12, we see another sort of nonlinear pattern where, yeah, more income helps, or excuse me, more education helps, but again, there's a big jump when you get to the next degree. So this type of trajectory, this type of pattern can be approximated by carving the predictor up into sections and fitting a separate slope through the different sections. So this is what's known as a linear spline model or a piecewise slopes model. And this type of application has a lot of uses, and I wanted to give you a chance to practice it. So this is the last part of your homework 4 that we have yet to talk about. Okay, so are you with me in concept? We're trying to fit like little sections here. Now, how to do that is the tricky part. So ultimately, what my goal is to fit a slope from years 2 to 11 that describes the effect of education among those without a high school degree. So if you don't have a high school degree, does more education matter? A second slope that describes the acute effect of a high school degree. So going from 11th grade to 12th grade, what is the concurrent change in income? And then for simplicity's sake, I'm only going to fit one more slope that goes from 12 to 20 that describes the effect of each additional year of education for those with at least a high school degree. So different slopes for these different regions of years of education. And the way I'm going to do that is by a different kind of coding scheme. So this coding scheme here, like the previous example, the original variable is shown in the first column here. So this is years of education. I need to create 3 new predictor variables in the same way that we created 3 group differences. So it's another 3 slope model, but just for a different reason. So I have a slope that's the name of the variable, I named it is less than high school, less HS. The second variable is graduate high school. It's the effect of whether or not you've graduated high school. And the third one is the effect of years of education if you've at least graduated high school, so over a high school degree. I chose to put the intercept at 11 years of education. So that was my choice. That's where I'm sort of putting the model reference point. What is income predicted to be for someone with 11 years of education? So because I want that as my reference point, I have zeroed out the 3 new predictor variables I'm creating at that point. Then we got to figure out what the coding looks like to get to the other values. Okay, are you with me so far? So 11 is my reference. The first slope, I want to convey what is the effect of an additional year of education specifically for those who have less than a high school degree. And because 0 right now refers to people in grade 11, if I want to compare grade 10 to grade 11, I put in a -1 because 10 is 1 less than 11. Likewise, 9 is 2 less than 11. If I had grade 8 in the table, that would be a -3, and so on. So this first column is going to be created as education minus 11 only for the people who have 11 or less. For the people who have greater than 11th grade education, I'm not talking about them yet. So they're zeroed out. The second column, the job of this predictor is to capture the acute difference of grade 11 up to grade 12. So it's zeroed out before we get there. It turns on for somebody who has a high school degree. So when it switches to 12, we switch it to 1. And it stays at 1 because all of these people with higher levels of education, I've got 2 16s in here for some reason, they have a high school degree also. And in the last column, I'm only talking about the people with greater than a high school degree. So it's zeroed out until I get to somebody with 13 years of education, in which case it is education minus 12 that gives me this last column. So each set of values is activated, so to speak, in a different region. The first variable captures differences in education up to 11. The second variable then turns on to capture the difference going from 11 to 12, and then it shuts off because the third variable picks up where it shuts off to capture further differences as a function of education after year 12. So this coding scheme is going to give me the ability to estimate different slopes through different sections of this education predictor. Okay, how are we doing with that? I've only got 2 faces left, so you guys are going to have to take it for the team. Represent the class. There's 3. Welcome back. Oh, there's 4. I didn't mean to shame you into having your cameras back on, but this is the problem with polling, right? You can only get the votes from the people who answer your poll question. Okay-ish. Yes, I think that's a good response. Okay-ish is good. The idea is that each of these slopes is only active, so to speak, only increases as a function of the variable in its section. It's shut off ahead of time or afterwards. So the first one is going to be active from 2 to 11. It shuts off after 11, so it takes whatever value it left off at as the 0. The second one is not active yet until we get from 11 to 12, but then it shuts off after that because I don't want it to index further changes in education. The further changes in education gets picked up by the third variable over here. The code to make this then, I'll show you for each program in isolation. So here's SAS. The 3 new variables that I'm creating go first. So I'm creating empty columns, less than high school, graduated high school, over high school, and then selectively filling in the values. And rather than just filling in zeros versus ones, I'm going to have to use functions to make sure that the values increase as a function of education. So if education is less than 12, that's what LT stands for in SAS, then do. So if we're at row 11 or lower, the first column is going to be the original education variable minus 11. So that will cover all the way from education of 2 years, which was the lowest in the sample, up to 11. The other 2 variables are shut off at 0 because they're not activated yet, if we're talking about someone with less than a high school degree. For the rest of the sample, so GE stands for not a refrigerator, but greater than or equal to. That way 12 is inclusive in the second set of transformations. So if it's greater than or equal to 12, then do. The first slope is shut off because I'm not talking about them anymore. I'm talking about the people with 12 years or higher. The second slope turns on to 1 because everybody at 12 years or higher has a high school degree, which is what the second slope is meant to convey. And the third slope is going to be your current level of education minus 12. So how much more than high school do you have? That's what the third slope is trying to capture. And a typo was 16 twice here. I'll fix this and repost. Sorry about that. But the logic hopefully is clear enough, even though I didn't mess up. I messed up the numbers. And so then those 3 new predictors go into the model, and each is responsible for its section of education. All right, SAS people, questions on those commands? I'll show you Stata in just a sec.
I have a question.
Yeah.
I don't understand why is it so I get the first one. It says, less than high school for Oh no, maybe I don't get the first one. So then for graduated high school, it's 0 and over high school is 0, and I get that. But then less than high school is 0 makes sense. But I don't understand, why is there a negative 12? Like, why negative 12? I don't understand that.
The negative 12 means minus 12. So it's taking whatever the original education column is and subtracting 12 from it to create the values that are shown in the table here. Because what we're trying to represent with this over high school predictor is how many more years than high school that you have. So 12 is kind of like the new 0 for that predictor. So among people with at least a high school diploma, how many more years than high school do you have? That's what I'm trying to get to with the over high school. And to
So
do
then
that, it's education minus 12. Go ahead, sorry.
No, so then whatever the residue or whatever is left over, that's what that means. Like how many years of college you have on top of high school.
Yeah, that's what it means.
Okay, thank you.
Yeah, so you can think of this as like different slopes for different folks, right? The job of the first variable, less than high school, is to differentiate amongst people with 2 to 11 years. The job of the second variable is to differentiate amongst people with 11 versus 12. And the job of the third variable is to differentiate amongst people with at least high school. So 1 more would be 13 years, 2 more would be 14, and so on. Here's data code. Same ideas, slightly different way of writing the syntax. First step is to generate 3 empty variables. That's what the dots mean, is missing values. And then replace what each variable is going to become with the conditional logic at the end. So if education is less than 12, then the first one is education minus 11 and the other 2 go to 0. And then the third 3 sets of commands is if education is greater than or equal to 12. So the greater than equal sign mathematically is the same thing as GE in SAS. And so then the values switch to 0, 1, or education minus 12 in the second half of the table, differentiating amongst people with 12 or more years of education. And the 3 predictors then go into the model. All right. Stata folks, questions on the code?
Yes, I'm sorry. I have another question.
That's all right. Go for it.
I'm not that I'm dumb, but like, why don't we make another replace for the, like, wouldn't they be 3 different replace?
In this case, I only needed to know whether or not you are in the 2 to 11 group or the 12 and on group.
Oh, okay.
I'm making 3 different variables, and that's why there's 3 different replace statements. So I'm customizing each of the 3 columns with its own line. But in terms of the caveats, or what's known as conditional logic, at the end of these statements, there's only 2 conditions that I would need to specify to cover every possibility in the table.
Okay, sounds good. Thank you.
Sure. Don't feel bad about asking questions. You're here to learn. You know, in the classes that I took, and even the classes that I audited as a postdoc, for instance, I went to further graduate classes. I was that person with my hand in the air like every 3 seconds. I annoyed the crap out of my classmates. And I'm not sorry. Isn't that what the kids say now? Sorry, not sorry. Because I learned this stuff and I live to tell about it. So never apologize for asking questions. That's the only way to get through this. Okay. Do you want to see what happened? Here's our results. So this is a 3-slope model. The F-test for the model is summarized right here. So I can show you where these numbers came from on the output in a moment, but just to remind you what these are telling you. So the 3, that term, that's numerator degrees of freedom, or degrees of freedom for the model. That tells you how many slopes went into your model. So there's 3 slopes in this case. Question, for our homework, is it sneaky and it's going to be 4 categories, or is the second part still going to be 3? In your homework, I am asking you to fit 2 slopes instead of 3. So it's actually less sneaky. Yeah, only 2. I'm asking you to take one variable and to basically cut it in half and to estimate a slope for the first half and a separate slope for the second half. And we can go over that next time if you would like to. I'd like you to give it a shot though. See if you can reason your way through the logic. But we can talk about that because yeah, this is one of the trickier parts of the class. But these types of models come in handy in a lot of different contexts. So the F test here, 3, 7, 30, that value is denominator degrees of freedom. That's always sample size minus the number of fixed effects in the model. This sample has 734 people in it. The model has 4 fixed effects. It has 4 betas, 1 intercept, and 3 slopes. So that's why this is 730. The F value, that 47, that is our test statistic. So I refer to this in shorthand as either an F value or an F test. That is a simultaneous test as to whether or not our 3 slopes are equal to 0. In other words, does education matter in predicting income? That's the question that this F answers. The way that education matters according to our model is described by 3 different slopes. Differences amongst people who didn't graduate high school, the effect of graduating high school, and the effect of post-high school education. So it took 3 slopes to describe education in its full form. But does education matter is captured by the 3 slopes. That's our test of the model. 47 has a p-value of less than 0.001. So yeah, these 3 slopes as a whole are not 0. They would be we would find 3 slopes as extreme less than 0.01% of the time if the true slopes were 0. That's what the p-value means. Very unexpected. MSE, what's that? Do y'all remember? I don't think this is a hand one, but if you can give me a hand signal for this, I'll be really impressed. Model variance, close. It is variance. Mean square error is what MSE stands for, or mean square residual. I would take either of those. Yeah, residual variance. Variance left over. One of you wrote this in your quiz, how much variableness is still there? Whoever wrote that made me laugh. I like that description. How much variability remains after controlling for education? 159. So that is reported for completeness. That way you could calculate all of the other sums of squares in that table if you wanted to. R square at the end of the line here, that's an effect size. So there's 2 different ways to think of R square. One is as the proportion reduction in variance after factoring in your model predictors. So in other words, 16.4% of all the variability in income, 16.4% of all the reasons why some people make more money than others has to do with education. I've got about 84% left over though, so education is clearly not the only story here. The other way to think about this R square is if you unsquare it, make it R. So the square root of 0.164 is 0.404. That's a correlation. More specifically, if I were to calculate a predicted y hat for each person as a function of their education, that predicted y hat column would be correlated with the real y column, 0.404. So R squared tells us in effect size terms how good our model is, how effective our model is. The test of whether or not that R square is significantly greater than 0 is the F test of the model. So our 3 slopes do work together to significantly predict variance in income. 16% is how much variance they predicted. Okay, Questions on that much? Okay. Then the parameters. Beta 0. Beta 0 is my fixed intercept. Beta 0 is always the expected outcome when your predictors are 0. Okay, what does that mean here? Because of my coding table, all my predictors are 0 when I'm at 11 years of education. That's the way I set it up. So somebody with 11 years of education is predicted to make about $8,500 a year. Beta 1 is a slope for what is the effect of education among those with 11 years of education or less. So moving from 2 years of education up to 11, what happens? The slope is actually negative. The slope is minus 0.3. It's non-significant. So if I move from 2 years of education to 3 years of education, I am predicted to make about $200 less. So for every additional year of education between 2 and 11, I'm predicted to make $200 less. So the slope is non-significant, but it's actually negative, meaning more education doesn't help from 2 to 11. And the standardized slope that goes along with that is very, very small. Beta 2, given my coding scheme, captures the jump, the effect of going from 11 to 12. As we might expect, there is a significant increase. So if you go from 11 years to 12, you're predicted to make about $4,600 more a year. That is a significant effect if we use our alpha level of less than 0.5. Standardized slope, though, is somewhat small. So on a correlation metric where it's minus 1 to 1, my slope is only 0.1. So that's a fairly small effect. And last but not least, the slope for the difference in income after 12. So let me back up. The third variable here is capturing differences among people who have at least a high school degree. If you at least finish high school, what is the effect of more education in those people? And it's about $2,000 per year past 12. And that is significant. So it takes 3 slopes to fully describe the effect of education according to this model. Now here's another picture. I have mapped what the model says versus what the data say the effect of education should be. So if I look for between 2 to 11 here, that matches pretty well. The data are the jagged black line. The jagged red lines are standard errors around it. The dotted lines are what the model says. Model also does a pretty good job from 11 to 12. But what do you think about the fit of our predicted line? So this is a linear slope. The dotted line is a linear slope because that's what we said it should be in our model versus the data. Thumbs up or thumbs down? How well do these match? Yeah, Nikki's emphatic, right? Thumbs down. Yes. It's the professor once said it's better to be wrong than vague in my graduate school. I always liked that quote. So yes, don't be vague. Thumbs down. Yeah, this straight line through all this jagged mess, that makes me uncomfortable. That doesn't look very good. It kind of looks like I need a different line that goes from 12 to 15, and then another one from 15 to 16, and then another one maybe from 16 to 17, and then 17 to 18, and then this. So that would take a bunch more piecewise slopes. I invite anybody who wants extra practice to try and fit the model and let me know what happens. I left it here though because I thought 3 slopes for a demonstration was enough for the purposes of this. So yeah, I'm happy with the fit up to 12. I think the fit from 12 to 20 needs some work. So if I were pursuing these analyses for a real publication, I would not leave it at this. But for the purposes of this class, I think that's enough. because I've got another example that we'll do next time. Okay, questions? Now in your homework, only 2 slopes. So actually easier than this. Will I upload the Excel spreadsheet I provided earlier in class? Yes, I will do that. So give homework 4 a try and let me know if you run into problems, and we can go over parts of it in class too. I'm happy to do that because this one is the most coding intensive of the ones that you've had to do yet. So getting the coding right is going to be the hard part. Fitting the coding in the models is going to be relatively more straightforward. All right, then should we call it a day? All right. Stay safe, stay sane. Let me know if you need anything. See you Thursday.
Lisa, I have a question.